So Arrow's impossibility theorem holds in the situation where F yields a ranking, and there the axioms are a little bit different. The axioms are, the first axiom is very much like unanimity. It's called sovereignty. And what that means is the population should be able to achieve the outcome that it wants.
What is the more general case that it yields a ranking instead of a vote? What is something more general formulation?
The formulation is more general. The axioms are not more general. Because now you have this extra axiom of independence of irrelevant alternatives. So for example, if under the same assumptions, also the fact that when you're generating an entire ranking, something is hard to do is less surprising than something is hard to do when you're trying to choose a single winner. In Gibberts-Hathaway, you're trying to do something simpler. You're trying to get a single winner, and it's still hard. And then the other thing that they want is that Arrow postulates is independence from irrelevant alternatives. So think of sovereignty as unanimity. If everybody agrees on a ranking, that's the ranking that gets output. Independence from irrelevant alternatives just means that the ranking of relative ranking of A and B that gets output only depends on the ranking of A and B in each person's ranking. Okay. So what that means is order of A and B in output. Is it clear what I mean by output? I mean the ranking that's output by F. Okay. Depends only on the order of A and B in input rankings. I mean, F is just a function. It takes rankings as input, produces a ranking. And so this is a particular, so this is a great example of axiomatic thinking, right? So these are Arrow's axioms. They take the norms that he has in mind. Sovereignty is a norm that people, if it's a democracy, people should be able to implement what they want. That's a norm. Sovereignty is an axiom, or unanimity is an axiom. This idea that you want to be fair to candidates. If I'm ranked above other people, then I should be ranked above them in the output ranking. That's basically what independence from irrelevant alternatives claims, right? And so, and then with these axioms, you get essentially impossibility. So what Arrow showed was that the only ranking system that obtains this is dictatorial. You pick there's some particular voter, and the output ranking is equal to that person's ranking. And so this is a very strong impossibility theorem. Yeah.
This basically, I can jumble up the order of all other alternatives.
Yes.
The relative order of A and B would remain the same in the output.
Yes. I can jumble up the order of all other alternatives. The relative order of A and B will remain the same. Right? There are other weaker forms of this which also lead to impossibility, but that also leads to impossibility. And so somehow it's the. No, it does not mean that everyone has to prefer A to B. Yeah. So I think this axiom is a little bit is not quite as obvious. Okay? And that's the reason I said that Gibberts-Hathaway is a stronger result. You get impossibility here, but it's not clear that this is something it's not immediately obvious this is desirable. Whereas if you're running an election and you want it to be non-manipulable, which is basically what strategy proofness means, that sounds very desirable. And the fact that you want unanimity sounds very desirable, and so which is why Gibberts-Hathaway I feel is a stronger result. So this is a great example of axiomatic thinking, and they don't always have to lead to algorithms. Sometimes they can lead to impossibility results, and then you can decide which of these axioms you want to weaken. Yeah. So in terms of Gibberts-Hathaway, the axiom that we don't really want to weaken any axiom. We want to make more modeling assumptions. The theorem is that any ranking system, any social choice function which uses a ranking, which satisfies sovereignty and which satisfies independence from irrelevant alternatives, must be dictatorial. So basically, f of sigma I, f of sigma 1, the only rules which satisfy sovereignty and independence of irrelevant alternatives are the form where given these input rankings, you take one person's ranking and that gets output. Doesn't have to be strategy proof. Yeah. So I think Gibbard-Satterthwaite, so the one way of thinking of the two is Arrow's impossibility theorem has sovereignty and independence from irrelevant alternatives. Gibbard-Satterthwaite has sovereignty and strategy proofness. And somehow strategy proofness seems to me like a more obviously an axiom that resonates at least better with me than independence from irrelevant alternatives. So that's why I think Gibbard-Satterthwaite is stronger. Also, there you're choosing a single winner, and even that's hard, right? So when you prove impossibility for a simpler task, that's a stronger theorem. So which is why I feel like Gibbard-Satterthwaite actually offers you more insight into the hardness of these problems. Yes? So the question is there a version of Gibbard-Satterthwaite where F fields are ranking? No, Gibbard-Satterthwaite is stronger than rankings. So I think you have to have this slight switch in your mind when you're thinking of impossibility results. Stronger things lead to weaker results. So Gibbard-Satterthwaite would be weaker if you had a ranking, not stronger. The fact that it's true for a winner means it's also true for a ranking. Does that make sense? Sovereignty is the same as unanimity. So sovereignty means that f of sigma 1, f of sigma comma sigma comma sigma has to be sigma. Yeah. It's slightly weaker than this, but let's say that. Sovereignty really means that there is some sigma 1, sigma 2, sigma n, which can yield to any sigma. So it's slightly weaker, but for all intents and purposes, you can assume that this is it. So with that in mind, I'm going to focus on overcoming Gibbard-Satterthwaite as opposed to overcoming Arrow.
So symmetry of the function that's never an axiom.
No, but I think, so Arrow's impossibility theorem is stated in many ways. So yeah, but symmetry is not something that's used here. No, dictatorship can be symmetric. No, I think but symmetry depends on whether you want symmetry in voters or symmetry in alternatives. And I thought what you were mentioning was symmetry in alternatives. Yeah. So dictatorship is symmetric in alternatives, even though it may not be symmetric in voters. Yeah. So I'm going to focus in this lecture. I'm going to focus on situations where you can actually overcome Gibbard-Satterthwaite. Yeah. And we're going to overcome it not by relaxing the assumptions, but making additional assumptions about what people really want. We're going to assume there's some structure on what people want. The rankings are not arbitrary rankings. We're going to restrict the class of rankings that people can have and then see what we can achieve. Okay? So the first thing, the first scenario in which you're going to look at is going to be the median voter theorem or Black's theorem or Black-Galton theorem. And this theorem lies in the following, this theorem applies in the following setting. Okay? The candidates, the set of candidates is just the real line. So there are infinitely many candidates now. Okay? So you can think of the candidates as being just points on a line. Okay? So imagine that there's a big highway, and you're trying to place a hospital on that highway. Okay? And the candidates are, every location at which you could place the hospital is a candidate. Okay? So, or let's just, it could be 0, 1, doesn't really matter. You could say the candidates lie on a 0, 1 line. So anything on this line is a candidate. Okay. I'm going to assume, yeah, there's total order on the candidates. Okay. I'm going to assume that voters have that each voter has a total ranking on all the candidates. Okay. Each voter I has a function ui, has a function ui which maps, let's say 0, 1 to 0, 1. Okay? And think of ui as the utility of this candidate for a particular point. Okay? And so ui could be sort of any curve. Okay? And by the way, this could be r, this could be r, is fine. The fact that 0, 1 is just incidental. And so, for example, I could plot ui, and ui could look like this. Okay? This could be ui. This would be an example of, so this tells you how much utility this user is going to get from each particular location. And as you can imagine, this case is, a general utility function is very complex. And anything that was going to happen in Gilbert-Satterthwaite, you can replicate with a general utility function. But we're going to make a specific assumption. We're going to assume that these UIs are single peaked. I'm going to also assume that n is odd for now. Okay, it doesn't really matter, but it's going to just make the illustration simpler. Okay. Sorry? Sorry, could you repeat it? M is infinite, yeah. Yeah. So set of candidates is the entire line. So M is actually infinite, yeah. So I'm going to assume that these utility functions ui are single peaked. And a single peak function means that there's a particular, so a single peak function is something where there's a single maximum. So ui is a single maximum. And it decreases to the left of the maximum and it decreases to the right of the maximum. It can decrease in any way, but it's monotonically decreasing to the right and is monotonically decreasing to the left. Okay, has a maximum and decreases here. And decreases there. Well, if it's decreasing continuous, it's monotonically decreasing, so it can't have any other local peaks. Right. Okay. So this is the situation that we are going to be in. Okay. And we're going to understand if in this situation we can devise a rule which is non-dictatorial, has unanimity, and is also strategy proof. Okay. In fact, we're going to actually find a rule that's not just unanimous and strategy proof and non-dictatorial, but in fact also is optimum in some sense. Okay. So these are the UIs. Okay. And so the question is, what would be can someone think of a good rule that you could apply in this situation? Let's say you're given the entire UI. Yeah. Yeah, you could take the average, okay, of all the so you could take the average of all the UIs. And find the point that maximizes the UI. That turns out to be non-strategy proof. Because what can happen is it incentivizes you to misreport your peaks as being very high. Okay? And so this is called like the squeaky wheel theory. So if you're going to take the average, what happens is I'll say, no, I really only want this. This is my utility. I'm really sick, and if you don't place the hospital right next to me, I'm going to like be very inconvenienced. You better place the hospital right at my house. Okay. And so average is not going to do it. There was a suggestion where you find the region where you have the maximum peaks. That's not going to do it either. I don't know if this name Galton. I guess the thing is you find the median of these peaks. And that's going to be a strategy proof rule. I'm going to show why it's strategy proof. Okay. So my social choice rule, my social choice function is going to be find the median of the peaks. Okay. Does that make sense? So I'm going to report I'm going to find the median of all the peaks, and that's going to be my social choice rule. Yeah. No, the peaks are, the peak is a single peak, so everyone has a single maximum. Yeah, so you take the n peaks, n are odd, and you find their median. So this is voter 1, this is voter ui. Yeah. So let's say this is voter ui, this is voter u1, let's say this is u2, and let's say this is u3. These are the 3 peaks you're interested in, so you pick this as your answer. So the set of candidates is continuous, but the set of voters is not continuous. Right? So the median of the peaks is still well defined. Now since you're only taking the median of the peaks, this rule has a property that you can only ask people to report their peak. They don't have to report their entire UI. And so strategy proofness here means, are people going to report their true peak, or are they going to misreport their peak? Does that make sense? So our voting rule is the following: instead of asking everyone to report UI, we're going to just ask them to report their peaks. And then we're going to find the median of the peaks, and that's where you're going to place the hospital. That's going to be our solution. And the claim is that this median of all these peaks, this rule is strategy proof. Okay? Now let's look at this particular case. So let's look at one particular voter, right? So the question is, will the same thing work if you're going to take medians in both dimensions? Yeah. So if you're single peaked in and you're decreasing everywhere away from your peak in every way, then this basically becomes 2 elections as opposed to 1 election, which is 1 for each coordinate, and then you can again show that this is going to be single peaked. So let's focus on one particular voter. Let's say this voter is, without loss of generality, let's say this is like voter UI. Okay? And this is the peak, this is the true peak of the voter UI. This is what's going to happen, right? Okay? And let's say that if this voter reports its true peak, then this gets chosen as the median. Okay? So what could this voter do? This voter could misreport its peak. Okay? So if the voter moves his peak right, then what's going to happen to the median? It's going to remain the same. It's not going to benefit this voter. If it moves his peak left, what's going to happen to this voter? The median is going to remain where it is. It doesn't matter, till the point where the voter reports a peak which is all the way to the left of the median. That's the only time the median can switch. Okay? Because for the median, all that matters is whether the peak is to the right or the left. But if the median switches because this voter goes all the way to the left of the median and makes this be the new median, then the voter is actually worse off. So the only way you can affect the median is by making yourself worse off, by putting yourself on the other side of the median. Right? So, and that gives you strategy proofness. You can never be better off. But there are situations when you can be worse off. If I move UI to here, then I can't be better off. But if the median happened to be in the middle, then I could be worse off. Right? And so as long as you have single peak preferences, right? So because it's single peaked, it's never helpful for me to have the median be further away from my peak. Does that make sense? This is where single peaked is important. If my peak were like this, if my utility were like this, then I could actually benefit by moving the median there, right? But if I'm single peak, then I'd rather have the median be as close to me as possible, and the only thing I can do is move the median further away from my peak. So this is it's a very natural setting, and the way to think of this setting is that what we have really done here is we have made an assumption on people's utility function. Earlier we had assumed that people have rankings, and rankings really is the same as saying that people's utilities are completely general. Okay? And now we are assuming some structure on voters' utilities. When you assume structure on voters' utilities, then you can sort of change exactly what you elicit from them, and you can also change your voting rule in a way to make it strategy proof. Now, in addition to being strategy proof, is there another property that this satisfies? This rule has, so it definitely satisfies sovereignty, it definitely satisfies or unanimity, it's definitely strategy proof, it's definitely non-dictatorial, okay, because you're taking the median of everybody. It also maximizes, it also minimizes the total distance between the chosen point and the peaks. Okay. So the median by definition, so the median has this property. Okay. The median will have this property. So let me say pi is the peak of ui. Okay. So saying that I want to find the median of pi, I want to find the median of all the pi's, is the same as saying that I want to find the point x, which minimizes the sum of the distances to all the peaks. Okay. So in some sense, I'm making everybody, I'm also somehow minimizing disagreement. Right? So remember, there's nothing in Gibbard-Satterthwaite that requires F to be a good rule or a fair rule or somehow utility maximizing rule. So this rule is not just, or a cost minimizing rule. This rule is not just strategy proof, it's also doing something which is very reasonable. So for example, for the hospital case, if PI is my house and all I'm measuring is how far is the hospital from my house, then this is actually the optimum solution to the problem, right? It's minimizing total distance that people have to travel to go to the hospital. Yes, the position of the peak. Yes, sorry, thank you. Yeah.
So when it comes to hospital choice,
Yeah.
I guess it makes sense to say that the further I am from my optimal thing, the worse I get. So the
Yeah.
seems natural. But when it comes to like voters and people,
Yeah.
does this assumption?
Well, not necessarily for voting for people. So it also does, not necessarily for voting for people, but it does make a lot of sense when voting for policies. So imagine, like it might sound like a little bit strange, but I need to take a quantitative example. Okay? So the quantitative example, imagine that in the US, people are trying to figure out at what week, before what week should you be able to have an abortion and what you shouldn't. So you can imagine everyone comes and writes down their ideal week, and you take the median of the ideal week. Okay? And so there are lots of situations where you're trying to choose alternatives, and there this completely applies. Right? But of course, in a fully general case, nothing is going to apply because of Gibbard-Satterthwaite. So you really have to start narrowing the domain where things apply. Yeah? So the question is, can you reverse this where your utility is as far away as possible? I don't think so, but I'll have to think about it. It would have to be, the thing with the median is well defined without really assuming what the domain is. Like I said, it's 0, 1, but it could have been the real number line, doesn't really matter. If you're placing it as far away as possible, then I think it matters, like, I mean, it becomes a bit more complex. I'll have to think about that. So it's definitely not single peaked. So I have a feeling it's not single peaked, so I have a feeling that it's not going to work out. So the other situation, which is very general, where you can overcome, so does this make sense? So this is a very clear, this is a very important and concrete example where you can overcome Gibbard-Satterthwaite. Yes? Yeah. So for a multidimensional domain, so imagine that you have single peakedness in every dimension. Right? So I'm not that good at drawing, but like in 2 dimensions, sorry, how do I draw this? Yeah, a contour plot, but I'm not that good at drawing these two. Like, is it clear what I mean by there's a single peak, and in every direction that you go is decreasing. Then imagine that you run 2 elections. So since these elections can be arbitrarily complex, I can ask people to report their peak. So Pi is now 2 points, AI, Bi, because there are 2 coordinates. And then my f of p1 comma p2 comma pn is just the median, is just the median of the AIs and the median of the BIs. Okay. And so because of single peakedness, people are going to report the correct AIs and the correct BIs because they want to be as close to this axis as possible in the x-axis in the optimum and the x-close is y. Now with more complex functions this may not be true, but for with a strong single peakedness the number of dimensions doesn't matter. Okay. What breaks down here is the optimality. Because it's not true, if you have an arbitrary single, it's not true that you are going to be able to minimize the distances. Or rather, maybe I should modify this. In one dimension, all norms are the same, or all LP norms are the same. When you go to 2 dimensions, then whether it's optimum or not depends on how you're measuring your distances. If you measure distances in the Manhattan metric or using the L1 norm, then this election in 2-dimensional election just decomposes along the dimensions and you get optimality. If on the other hand you're going to measure distances in the L2 norm, then while single beacon is still enough to give you strategy proofness, it will not give you optimality. No, it's weaker because you just need it to be decreasing in every direction. You don't need it to be concave or have any particular kind of gradient. Okay. So, but would this be quasi concave or? And this too. Yeah. Okay. Then I guess yeah. So as long as it's monotonically decreasing in every direction, I think. Thank you. So then, the other direction, the other important area, and so this one I'm going to dig into a little bit more and give you an actual concrete example, a concrete real life example, and that would be a good segue where we'll move from classical results to new research results, would be what's called approval voting. In approval voting, I'm going to assume, and once again these are, because we have Gilbert-Feather weight in general, we have to make some strong assumptions on what our domains are. I'm going to assume that each user, again has a utility function, I'm going to assume that the set of candidates is now again discrete. Some finite set S. Okay. These are my set of candidates. Okay. I'm going to assume that each voter has a utility function which maps S to 0, 1. What that means is that for each voter, there's some candidates which are acceptable, and those are going to be assigned a utility of 1, and some candidates which are unacceptable, and those are going to be assigned a utility of 0. Okay. And this happens quite often in choosing committees. Often what happens is someone might go and say, okay, can you tell me all the people who are acceptable to you as chairman of this committee, or chairwoman of this committee, and all the people who are not acceptable. Okay. So this is, so is the utility function clear? Okay. And so this is this is the utility that people have, and all that people care about, right, is whether one of the people that they like gets chosen or not. So in particular, I can define SI as a set of all candidates C in S such that UI of C equal to 1. Okay. So SI is all the candidates that are acceptable to this voter I. Okay. Is this clear? So UI is a utility, SI is a set of acceptable voters, right? And so the election that we want to run is that we ask every voter to reveal SI, and then the social choice rule will choose a single winner, and we want to make sure that every voter reveals the correct SI. Does it make sense? the election we are going to run is called approval voting. And these sets SI are called approval sets. All the candidates that this voter approves of. And so in approval voting, every voter reveals SI. Okay. And F, which is the election rule, chooses the candidate in the most elections. Does that make sense? In the, sorry, the most SIs, yeah, in the most SIs. And so this is approval voting, and this turns out to be strategy proof. And first of all, it's clear it's a very reasonable election, right? It's an election that's, is it clear that this is an election which everyone reports their SIs truthfully, then this is an election that maximizes utility, right? Because you're choosing the one that's acceptable to the most people. Yeah. And so if I assume that the utilities are truly 0, 1, then approval voting maximizes the total utility. So that's what it means is that it's welfare maximizing. Right? So it gives the most welfare to the society as a whole, and it also turns out to be strategy proof. And its strategy proofness here is simple. If what can a voter do? A voter can misreport their set by either adding something to the set who's not already there. But why would you do that? That can only help this other candidate win. Or removing something that you approve of, which can only hurt you. Okay. So welfare maximizing means that you're choosing argmax over all candidates in S. So among all the candidates that are allowed, you're choosing the one that maximizes the sum over all the voters I of ui of x. So this is this quantity, sum over all I equal to 1 over n of ui of x, where x is the chosen winner, is called the social welfare. Which is basically how much total utility you're providing to society. Okay. So in this particular case, approval voting turns out to be both welfare maximizing and strategy proof. Assuming, this is a very strong assumption, we are assuming that UIs are of the form S going to 0, 1. Okay. So every result which goes, which says anything about strategy proof in elections is going to have some specific strong assumptions about utility, just because Gibbert's average is so strong. Okay. So in a way, it's quite surprising, and it's like a big celebration of the field of social choice that such strong results exist in such natural settings. Right? But they'll all come with strong assumptions, and that's a consequence of Gibbert's other weight. Yeah. Yes, I think there are sort of results which are more market oriented. So for example, you could imagine a situation where you're running some kind of a market, and I give people some prices, and if people are myopically strategy proof, I tell you that it's going to cost you $5 to vote for this candidate and $2 to vote for that candidate and $3 to vote for that, and you can vote for 2 candidates, but you only have $5. You can do things of that type. And if you assume some kind of myopic strategy proofness, then you can get. In fact, we are going to show one example where you're going to get weaker strategy proofness. Then there are results like envy-free. So in general, this non-strategy proofness has been explored more fully in the context of allocations. So especially in this, for this audience, right, the kind of problems that people might be more used to thinking about are allocational problems. You're given a bandwidth, you're given a server, you want to divide that server, the capacity of that server among many connections. Okay? And in social choice, you're making a single decision for everyone. Okay? So typically, when you're thinking about allocations, and you want to go beyond strategy proofness, you have things such as you can say, well, it's not strategy proof, but is it envy free? In the sense that, like, am I worse off than the other guy? Do I really want what the other person got? And then you can come up with sort of envy free allocations, and the equivalence to that here, and we'll see some of those equivalents as we go along. How much time do I have? 20 minutes? Okay. If the utility function is not just binary, then it's fully general. Gibbert's-Hathaway applies. Yeah, there's nothing that's not. No, for general utility functions and general rankings, they are essentially the same thing. And so, because general utility functions and general rankings are the same thing, because the ranking really says that I really prefer anything in my ranking who's above my ranking, I prefer it more than anybody else. And so you can make a big step function, and so it's all the same thing. I haven't seen those results. No. My guess is that as long as you have some combinatorics, you can recover Gibbert's-Hathaway. That would be my guess. So you really need the 0-1 property. As long as you can sort of misrepresent something and benefit, I think you're going to have. So the one way in which it does extend is that instead of choosing a single candidate, if you're allowed to choose 5 candidates, okay? So you're choosing like the board of supervisors for a school or for a university. You can say, instead of choosing the candidate in the most SIs, you can choose a candidate in the most SIs, throw that candidate out, then choose the one in the most SIs, throw that out, choose the one in the most SIs, throw that out, and you keep repeating it. That's going to be still strategy proof and welfare maximizing. Okay? So it extends. It doesn't extend to more general utility functions, but it does extend to more general choice functions. Yes? Yeah. Yeah. Yeah, so the question is there a notion of complexity of use? Yes, indeed. So instead of use, you can think of, say, disutility. And there are lots of characterizations of if your cost function or your loss function looks like this, then can you get strategy proofness? Can you get approximations? Yeah, it's a big, so what we have seen is just like the two simplest possible situations that are known. There are more complex situations known. And in fact, we're going to see, we're definitely going to see one of them, and I think we're going to see 2 of them. Yeah, that's basically what Gibbert's-Hathaway says is that you have to basically play this game of, for specific situations, what use can I get away with? So this is based on some work that we did before. It's called participatory budgeting. And the reason I'm describing this is because it connects very well with approval voting and with everything that we have done before, but it's also like a real life application. So this is something that actually happens in real life. And the way it typically happens is via something that's called K-approval voting. This is not strategy proof, even though it might sound like something that I already described. A set of proposing spending projects get put to the ballot for residents directly. Okay, a bunch of cities do it. Spain does it in many places. In the US, New York did it, Seattle did it, A bunch of them use a platform that we have for voting. So we have a platform that people can use for voting on participatory budgeting elections. A bunch of them use our platforms. For the first time, I think next month, the city has indicated that they're going to also use our algorithms, our suggested election mechanism, which I'm going to get to in a minute. Okay? So sort of proposed spending projects get put to the ballot for residents directly. Each voter chooses K projects for a fixed K. And the projects that get the most votes get implemented subject to a budget cap. So it might be a budget of $1 million, you start going from the top. Okay. So it's like approval voting, but it's a bit different than approval voting because you're approving projects, you're approving K projects, everyone gives K projects, and then you're sort of going down the list. Okay. And so we have a digital voting platform which was used in Chicago, New York City, Long Beach, Vallejo, Boston, Cambridge, lots of places. Also one place in Canada. Nowhere in India, even though I tried. And so basically people go and they choose, there's a money amount for each thing and they choose it, right? So here are the problems with K approval voting. Some of them I'm going to state informally, some of them you'll be able to see a formal thing, right? There's no recognition of trade-offs in this system, right? So there's no, it's a wrong question to ask, is it better to build a fountain in a park or fill a pothole on a street? It's a better question to ask, is it better to build a fountain for $10,000 or fill a pothole for $1,000? Because then you are really sort of taking the cost into account. Then this K approval voting is very strange incentives, and that leads to the question that was being asked here. The strange incentives, there exist cases where a strategic voter, a voter who's trying to maximize their own utility, should vote for A over B, even if she prefers B and B is winning. So like you go to a horse track and you're a sentimental favorite, and you know that horse is going to win because you can look in the future, but you bet against someone else. Okay? That can happen here. There's a particular candidate that you want, the particular project that you really want to win, and is winning, but you might vote against something else. Okay? And then the aggregation, was it rational for choosing projects? People are voting for K projects, but the budget is completely misaligned with the fact that they're voting for 4 projects, right? There's no alignment. So, sorry? Sorry, you go ahead.
So basically, it's like a multi-objective voting where you have preferences, but you have also a budget.
So there's a budget, the city has a budget. Voters have a utility function. We assume voters have a utility function UI on each project, yeah? Yeah. Independently of the budget. And the election, the way the election is run is that everyone can choose K projects, which is completely independent of, say, how much budget there is. And then the city goes and sees which project gets the most votes, runs that, then sees, okay, which other project got the most votes, runs that.
So basically, you say that you try to find a voting function that would satisfy the constraint of budget.
You have to have a voting function that satisfies the budget constraint, right? Yeah. And so, but it's not obvious what that voting function should be. Okay? And so that's another difficulty with this K approval method. It doesn't lead to a natural way of aggregating everyone's votes. So what we realized was that all budget problems are knapsack problems. And so knapsack problem is where you have a knapsack. The knapsack has a capacity. In this particular case, the capacity of the knapsack is just the amount of budget that's available to the city. Every project has a cost, which is known to everybody, and a utility, a societal utility. And think of that as the sum of the utilities for everybody. And you want to pack as much utility as you want in the knapsack without exceeding the knapsack limit. Okay? So given this way of thinking of voting, is it obvious, what are some of the obvious difficulties? Yeah. Yeah. So it's not. So first of all, it's not obvious where you get these utilities from. Okay. Where do these utilities? I mean, I said the utility of that project there is 50, the one that cost $200,000. How do I know it's 50? I mean, who tells me? There's no one. These utilities are not. The cost of a project is generally well known. Is utility? There's no numeraire. There's no denomination in which cities express utility when they're trying to decide what projects to do. People don't express utility. If I were to ask you, what's your utility for sending your child to a private school or a good engineering school as opposed to, say, buying a Mercedes, I don't know whether you'll be able to articulate the utility of each thing. You might be able to decide which one you would rather do, but it'll be very hard to articulate the utility of each thing, right? So first of all, people are not used to articulating their utilities, so it's hard to extract it from them. There's no common denomination. It's not clear how to add them all up, right? So it's very hard, even though this is a good model, it's hard to get these utilities. So what we said was, well, people can't really articulate their utilities, but people are used to making budgets in their daily life. Everybody gets a salary, they decide how to allocate their salary among the different things, right? So, well, why not just ask people to solve the whole knapsack problem and give us a solution to the knapsack problem? Okay. So you ask everyone to basically solve the knapsack problem. There are a bunch of projects or a bunch of things. They can allocate money to each project by making a slider. There's a bar at the top which tells them how much money have they already used up, how much money is left. Everybody is allocating the whole money. So everybody is solving the complete knapsack problem. Okay. And people can do it fairly easily. They don't have a hard time just because this is the way they do their own budgeting in their mind. Okay. And then no, so right now there's no K constraint. Now the constraint is just that they cannot exceed the knapsack capacity. Yeah. It becomes like utility 0, 1. They're either going to put something in the knapsack or not in the knapsack. And that question, the question was, is it become like utility 0, 1? Yeah, that question is prescient in the sense that under a very similar assumption about as the utility function, we show that this knapsack voting rule leads to both strategy proofness and social welfare maximization. But again, we're going to have to make some strong assumptions, just like we had to make strong assumptions to get approval voting to work.
From the point of view of human effort, is there an idea of how many items these spaces usually have people solve?
So we have done these experiments a lot, and people can solve knapsack problems fairly easily up to 25, 30. We haven't actually done more than 25 or 30, so we don't actually know. But my guess is that anything that you can read, you can solve. Because a very obvious thing to do is, even if you're doing approval voting or whatever, right, ranking, you have to read through everything. And so the way you would do it is you read through everything and you mark things that you could potentially like. And then you go and solve the knapsack problem on that smaller set. That's also how a lot of cities do rankings. If there's a city in Canada which did ranking using our platform, and the way they did it is choose the top 5, and then you choose the top 5 and then you go and rank them. Yeah.
The way we are solving knapsack problems, you to be there doing some sort of prioritization of choices.
I don't think so. So I think, because I think a full ranking is much more informative than a knapsack. A knapsack is like more like a threshold. So a knapsack formally a knapsack problem, if we ignore the issues of integrality versus fractionality, then a knapsack problem is formally the following. You arrange every project in decreasing order of bang for the buck, and then you find a dividing line. Solve a knapsack, you just understand whether something is above the dividing line or below the dividing line. So you're really solving an easier problem than ranking. So for example, I don't actually, for most of us, I think, I mean, given the fact that we're here, we can probably all afford to both eat and wear shoes. And so I don't think if anyone has ever thought about what's more important for them, have a coffee in the morning or shoes in the night. But it's possible that a lot of us have thought about whether it's important to buy a better car or pay for a more expensive education for their child, because that might lie at the marginal for a lot of people. Yeah. Yes. Yeah.
But is there a more systematic way to explore the design space itself? Somebody else may come up with a different design.
Yeah. Yes, I think that, so also it's easy, I don't know how to systematically articulate the design space, but to compare different designs is relatively easy. So for example, you could ask questions like, are these strategy proof or not? How close do they come to social, how good an approximation do they for welfare? Plus you have a lot of empirical data. So you can say, well, and you can run experiments and say, if I ask people to vote using this method or that method. Which one leads to an outcome that people like more?
So, for example, here is another question that you could ask.
Yeah.
The budget is 1 million, what would you want? The budget is 5 million, how would you set up the budget? That's actually additional information that you're getting from the individual.
Yes.
So I can come up with an institute of such designs.
Yeah. I don't know how to list the design space. Given two designs, I think we understand very well how to compare them. We haven't really succeeded in sort of. So I think what you're looking for is like some kind of an axiomatization or some kind of like a parameterization of the design space, saying this is the entire design space. We don't know. It's a very important question, but we don't actually know. So then, how do you aggregate things? So the aggregation rule turns out to be very simple here. Okay? And the aggregation rule is, suppose we are given a budget B and there's a set of projects P, and let's say each voter gives some amount of money to each project, so that the sum ends up being B. So we think of these projects, each project as being made up of many single dollar sub projects. So if I allocate if voter B, let's say allocates $3 to the project 1. We're going to pretend that what voter B really did is they voted yes for project, the first sub dollar for project P1. They voted yes for the second sub project, voted yes for the third sub project, and they voted no for the fourth sub project. Okay? So the voters are not actually doing it. We are interpreting their votes as being for these single dollar sub projects. Okay? And then you run approval voting on. So basically now what everyone has done, given you as an approval vote. Okay? They happen to be all the same size, exact size B. Okay? And then you choose the B that are the B sub-projects that get the most votes, and that's your outcome. Okay? Because no one ever votes for the fourth dollar for a project without also voting for the third dollar for a project. Right? When you choose the ones that have the most votes, you don't get any bizarre behavior. And so here you get strategy proofness with some very specific kind of utility. And like I mentioned, you have to have a specific utility functions to get strategy proofness. Yeah. So please ignore the first couple of bullet points. Let's get to overlap utility. So if a voter wants, the overlap utility is the following utility function. If a voter wants allocation X for a budget item, and the final chosen budget has an allocation Y for that item, then the voter's utility from that item is min of X comma Y. I wanted $1,000 for fixing the roads, you only gave me 80, my utility is 80. I wanted $1,000 for fixing the road, you gave me 2,000, my utility is only 1,000. I only wanted 1,000, the rest of it is not useful to me. Okay. Now I am not defending this utility function as being the best possible or in any way. The only excuse for having a utility function of this type is Gibbard said the way it tells you that you have to have strong assumptions on utilities if you want strategy proofness. And so with this utility function, truth telling is a dominant strategy. So basically what this is saying is that because of this $1 sub project, what this is really equivalent to is people are doing approval voting on sub projects. But people's utilities, I'm assuming that people's utilities happen to be such that they have utility 1 for exactly B things, where B is the budget, and they have utility 0 otherwise. And at that strong assumption, this is truth telling is a dominant strategy. A voter cannot increase the utility by misreporting a preferred budget. Right? So as long as you assume that people's utility is this truly the overlap utility, they have an ideal budget in mind, any deviation from that budget they don't like, whether it's you give them more or you give them less. Yeah. Then truth telling is a dominant strategy, and this is welfare maximizing. Yes. No, they're allocating specific amounts of money for each. Or they could say, if in the case the projects are discrete, if I'm choosing a project which costs 100, it means I want an allocation 100 for that project. If that project gets chosen, I get utility 100. If it doesn't get chosen, I get utility 0. So this allocation rule assumes that these projects are fractional. So it's assuming that I can do projects fractionally. And the allocation rule is the following. I'm going to imagine that each project is broken up into many sub-projects of $1. Okay? Everything is a $1. If I vote $5 for a project, I'm allocating $1 to each of the first 5 sub-projects of that project. And I just run I just run approval voting. The way I'm aggregating is exactly the same as approval voting on these sub $1 things. So basically, but because there's no way, if this is the first dollar for project 1, this is project 1, this is the first sub-project, P11, P12, and so on. I cannot, because I can never vote 1 for this without voting 1 for that. Because in reality, I'm actually allocating the amount of money. Therefore, when I do my approval voting aggregation, I'm going to choose this before that and this before this, and so there's no contradiction. And again, saying that this is I have this overlap utility is exactly the same as making the approval voting assumption, but further assuming that the size of SI is exactly B in terms of these dollar sub-projects. Everyone has utility only for the things that they're going to put in their knapsack and nothing else. Okay. And on that strong assumption, this is both strategy proof and welfare maximizing, okay. Which is not like the ideal result. You would want it under weaker conditions, assumptions on utility, but still something. Okay. Yeah. Yeah.
So everybody's solving an abstract problem. So what you're asking for is what is your solution, and I'm writing that in something.
Yes. 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 So I'm asking everybody. So the question is, what's the basic thing that's happening? What's happening is I'm asking everyone to solve the knapsack problem. I'm going to interpret their knapsack votes as an approval votes on single dollar sub projects, and then I'm going to solve the approval voting problem with exactly the budget that I have. And my claim is that there's going to be welfare maximizing and strategy proof. If I make the additional assumption that people only have utility for those things that they put in their knapsack, they have exactly the same utility for everything that they put in their knapsack, and they have zero utility for anything that they did not put in their knapsack.
Are you also, in the process, are you asking the voters to vote for the budget for each one? Is that what you're saying?
So, yeah. So the question is, are we asking people to vote for the budget for each project? So first of all, I'm assuming that these projects can be done fractionally. Okay. I'm not, the results apply in both settings. The results apply both when people, when these projects are, when people are voting either on full projects or when people can actually change the amount of money for each project. So you've run both kinds of elections. So if there are kinds of elections which says, how much money do you want to allocate for fixing roads? And the results hold in that setting, where people can choose how much money to allocate for fixing roads. The results also hold when people are asked, do you want to put this fountain in the park or not? In both cases, they have to stay within the budget.
You have to exactly fill the knapsack, right?
The voters don't have to exactly fill the knapsack. The system will exactly fill the knapsack. And the system will assume that it can allocate money to projects even if it's fractional. So the last project becomes a bit funky, but the last project that you fill. But there's no assumption here that the people have to fill the knapsack. They cannot go over. Yes, yes. So I think instead of, I should really have said that the size of SI is less than or equal to B. Yes. Yeah. Yeah.
So it is possible that one of my things get into the final approval, but others will not be selected.
That's correct. Yes. That's very much possible, yeah. And so under this strong assumption, right? So first of all, under this funkiness about fractionality, that the system is allowed to choose the final thing fractionally, and the fact that I'm making this strong assumption that the utilities are 0, 1 and they're less than or equal to B. Under these assumptions, the system is truthful and welfare maximizing. Okay? But then maximizing overlap utility is equivalent to minimizing the L1 norm between the chosen budget and the original budget. So if that helps you think through what this looks like. Yeah? Yeah. So it's also truthful if the penalty perceived by a user is the total disagreement between her ideal budget and the final chosen budget. I should put an asterisk here. This is under some asterisk. Sorry, go ahead, please.
What is actually the original budget numbers? Is there some gaming with respect to that?
Yes, so there's yeah, so I think these things like, so we are looking at a narrow view of strategy proofness. where voters are choosing which among the projects that are on the ballot. There's a lot of strategizing which happens in choosing the budget. So as an election designer, so there's another view of strategy in these elections, which I'm really glad you brought up. So the question is, are there other strategic things that could happen here? And I'm glad you brought it up, because I'm narrowly focusing on the strategic behavior of the voters. But really, in a democracy, you have to worry often also about the strategic behavior of the election maker. And by choosing, and that's a whole can of worms. So by choosing the projects which get on the ballot, by choosing the amount of budget that you allocate, then often by choosing the order in which people vote, especially in committee elections. So in committee elections, we can structure a committee in a way in which someone comes and declares their vote, one person of your department comes and votes, and the next person votes having seen the first person votes, and the next person votes, the next person votes, and everybody votes sort of, now that I know how you voted, I know some candidate is not going to win. So I'm going to change my votes. And so election manipulation by the election designer is a much thornier problem. And this is definitely subject to all kinds of election manipulation, assuming I understood your question correctly. Yeah. So and then under arbitrary additive utilities, where we assume that people's utilities are not 0, 1, but for every project they have an arbitrary utility, the best response of a user to everyone else's vote is weakly strategy proof. And so what that means is, if A is winning and I want A to win, I will put A in my knapsack solution. Okay? So this is a weaker version. It's not really full strategy proofness, right? But it's at least something. And once again, because of Gilbert-Sutherland, you have to be satisfied with half results. And so I think this is all I want to say for knapsack voting, except for the fact that the system exists. A lot of cities use it. If any of you sees an opportunity to use it either in a university setting or in a city setting or in a social, in a non-profit setting, please do let me know. Our platform is like free and open to use, and it's at pbstanford.org. And tomorrow, I'm going to talk about more complex elections than the one that we talked about today. Participatory budgeting. Thank you.